But let me say something quite general about the addition of angular momentum that you should kind of keep in mind. So we have these Clebsch-Gordon coefficients. And the way to think about those, they are coefficients that allow you to expand a tensor product space, which rotates in a kind of funny way under, the rotations. So it lets you take a space, which is, we can label it with these D matrices. Remember, D corresponds to a rotation of a particular angular momentum quantum number, like J1. Well, we had a tensor product of these, and this is what addition of angular momentum is really all about, right? You have these spaces that are tensor products of two different angular momenta states. And the whole point of the Clebsch-Gordon coefficients is that it allows you to take this space and it decomposes it into a set of irreducible representations, which, again, that's an important quiz question, so fill out the quiz. It reduces this space to a sum of spaces, meaning every element in here can be written as some linear combination of states in the following set of spaces, right? The set of spaces is the total angular momentum spaces labeled by J, the total angular momentum quantum number. And that total J ranges, from J1 plus J2 all the way to J1 minus J2. And it's the Clebsch-Gordon coefficients that connect you from this basis, which is not a good basis because it's reducible, meaning that the states in there, they all rotate into each other, and there's pieces of that space that actually secretly don't rotate into each other, but you can't tell because it's in a bad basis. It reduces, it breaks up this space into a set of spaces that all maintain, that where all the states rotate into themselves and not amongst each other at all, right? So this J here, the total angular momentum, it labels the irreducible representations of the rotation group, because we know that all of the real, the irreducible representations are all labeled by this J, and then there's an associated number of M's, right? So like J equals 0, that's the sort of trivial representation. It's just one state. It doesn't rotate at all. It just stays there like a scalar. Then there's the J equals 1/2, right? That's the spin 1/2 particle. That's an irreducible representation of the rotation group that rotates like SU2. It rotates like a little spinner, like a qubit space, right? And there's the J equals 1. That has 3 components, right? M is equal to plus or minus 1 and 0. Those states rotate like vectors, 3-component vectors, right? And then there's more of them, and each of those J's labels the irreducible representation. And so what we do here in addition of angular momentum is we have 2 of these angular momenta that we're adding together, 2 of these irreducible representations, but we're tensor producting them together. And that messes up the irreducibility, right? Because the 2 tensor product things start rotating into themselves. And so you need to be able to break that up into components that are irreducible, that correspond to their own fixed J. And that's what we're doing here. And that's what the Clebsch-Gordon coefficients do. So that's why they have this form. So I always remember what the little indices are. You add J1 to J2, which have their associated M1s and M2s, and you get out something that's a total angular momentum J and a azimuthal number M. So that's the form of these things. And so what's the Wigner-Eckart thing all about? Well, the Wigner-Eckart thing uses this stuff to try to understand what happens to two operators that also transform like these guys under a rotation group. Remember, we had scalar operators and vector operators. Well, you could also have just like a T operator that transforms like JM, right? It can rotate. So there's, you know, a separate operator for every, you know, value of J and M we could have here. And it's just the same, but the analogy is just like having, you know, TX, TY, TZ for the vector operator. Except now the components are not the Cartesian components, they're like the spherical harmonic components, you can think of them, or rather the angular momentum components. But they still, the whole point is that T rotates according to the same rules as the JM states. So the point of the Wigner-Eckart theorem is that it tells you how to compute matrix elements with respect to other angular momentum states. It just lets you compute things like this. Right, it lets you compute these matrix elements, which is useful for things like studying transitions or particular Hamiltonians, which you might be able to write in terms of these spherical tensor operators. And then these might be like the energy eigenstates, right, or related to the energy eigenstates. And then this will tell you something about the expectation value of particular terms in your Hamiltonian, you know, with respect to certain energy levels. So it can tell you about transitions between energy levels. And we'll see that next semester because we haven't really done any applications, but that's what it's used for. You might want to know, like, when are these matrix elements non-zero? That would tell you something about when these operators mediate transitions between this state and this state. And we'll see more of that later, but that's the general idea. And the general idea of how to do this is you just look at this object right here. This is something that, you know, looks an awful lot like a tensor product, right, in terms of the rotations, because this part rotates like JM and this part rotates like J prime M prime. And so the idea is, if you have this object, you know, if we only care about the rotations and it rotates like J prime and M prime, you know, and that's just, if we define it as this state, we just define it this way, then the idea is that we can use the Clebsch-Gordan coefficients in order to rewrite this state, right, as a linear combination of irreducible representations of rotations, which are labeled by alpha n here, where alpha is like the total J, and this is like the M or whatever for the total. And then here you'll have some coefficients, which will be the Clebsch-Gordan coefficients. And so then you see, it's, once you decompose this part, when you sandwich it with J double prime, M double prime, right? Now these guys, they're going to be written in terms of, you know, nice quantum numbers like this, the total angular momentum and the azimuthal number. And now we can do these inner products. That's easy because we know that these guys are orthonormal, right? They have to have the same J and the same, it's the same kind of basis, right? It's the same JM basis instead of something like a M1, M2 basis. So that's the basic idea, but it's better to just show some examples, I guess. And then I'll state the theorem again. So for example, we had the scalar operator. S. If we think about that, right, what is the matrix element? What is the matrix element here of J prime, M prime, S? Jm. Well, that's easy because we know it's a scalar, so it's actually, it doesn't rotate at all under rotations, and moreover, it commutes with J squared. So you can make S have the same, you can diagonalize J squared and S simultaneously. And moreover, S commutes with the Z component also. So it's pretty easy because a scalar doesn't rotate at all. So then this thing must be just equal to, since it doesn't rotate, this thing must be independent of M. So the only possibility is it's diagonal in M. It's also diagonal in J because this must be simultaneously diagonalizable with just the JM states. And so all you have left over is just the reduced matrix element, as it's called, of S with J. It just depends on J, right? Because remember, J is the part that doesn't change under rotation. So there, this would be like the associated eigenvalue of S for one of these JM states. And so this is like this is like the simplest version of the Wigner-Eckart theorem. It just tells you that, if you have a scalar operator, which if you want, a scalar operator is just like T00, right? It's the J equals 0 state. There's only one of them. It's the one that doesn't rotate at all. It just sits there. And this must be what the matrix elements look like. They must just be diagonal in J and M. And whatever's left over here is just, whatever that scalar is equal to for that particular J value. So, okay, so what about, how about these operators, the 1 M's? These guys are the vectors, right? And, or the spherical vectors. And if you recall, so we're going to call these V's. We're going to call them, V0 and plus or minus 1. And because they're related to the vector operator components, namely for a Cartesian vector operator with these components, you have that V0 is just equal to VZ. And V plus or minus 1, these are like the left-handed and right-handed circular polarizations that we looked at back a long time ago when we were looking at photon polarization. It's given in terms of the X and Y components of the associated Cartesian vector operator like this. So it's just some linear transformation acting on our Cartesian vector. And how do these things transform under rotations? Well, it's very easy. They just transform with the D matrices. Remember that these spherical tensor guys, they just rotate like the angular momentum eigenstates. But of course, they're operators, so the transformation rule here is U, the unitary associated with the rotation, and now VQ, one of these guys, the spherical tensor component, U dagger R is equal to sum over Q prime D1 Q prime Q R V Q prime. This is a transformation rule for a spherical vector operator. So how do the Clebsch-Gordon coefficients come into here? Well, it's easy. Again, the idea is we're going to try to expand this kind of thing, the vector operator acting on one of these angular momentum states. We're going to try to expand this in terms of the nice basis of total angular momentum. So how we do that is we say, well, first of all, we look at what the U's do to VQ acting on, say, a JM state, right? What does this do? Well, we can insert in U dagger U to get, U VQ U dagger U acting on the JM. And now we know everything about what this is. This U can act on this JM. This guy obeys this transformation rule. And so this thing is sum over Q prime D1 Q prime Q. I'm just copying this part. I'm going to drop the dependence on R, and it depends on the rotation that you're interested in. But this guy transforms like dj, right? Because it's angular momentum j. And then it's m prime m. Of course, we've got the vq prime here from over here. And here we've got the j m prime, right? Right, so we're rotating the JMs. That gives us this D matrix, M prime M, sum over these JM primes. If you go back and see how we define these unitary operators in terms of rotating these angular momentum states, you'll see that that just comes from that. Then we have this transformation wall for the spherical tensor piece. And so you get this, and if you look at this, what does this tell you? What is this telling you here? It looks like you have two different Wigner D matrices, right? One has J1 and one has just J is equal to J, right? So this object right here, this thing, it's transforming like one of those bad vector, like one of those bad bases, right? This is transforming like a tensor product of a spin 1 and a spin j, right? Because you have two of these D matrices and they're acting on the spin j part and the spin 1 part. So this thing is transforming exactly like 1j QM, right? QM, right? This is like in the M1, M2 basis, right? So that's nice because we know that we can write this kind of state, right? This state in the bad basis. We can write it in terms of the good basis using Clebsch-Gordon coefficients. In particular, 1j, again, this is like J1, J2, M1, M2. QM, that's equal to a linear combination from, J bar now from J minus 1 up to J plus 1 of C1J, QM, J bar, M bar of the nice basis, JM, the total angular momentum. So we can do that. We can now replace this guy with this linear combination of Clebsch-Gordon coefficients in this nice basis. And if we do that, then everything is kind of worked out. So if this piece right here, we now saw that we see that we can expand it in the nice basis. Then we can start taking the matrix elements of these guys, right? Now I'm just dropping the primes, and what this must be, right, is a sum over J bar, the same limits here, of these Clebsch-Gordon coefficients 1j QM, J bar, M bar, and now it's the inner product between J prime, M prime, which is the nice basis, with these guys, which are, again, I'll put the J1, J2 back. It's 1J, you're adding these two together to get J bar, M bar. And so, but it's important that this state, it actually secretly depends on what V is, because we're just noticing that this object transforms under rotations like this object. So maybe I could put a little V here, saying it's still dependent on the particular choice of the vector operator that we're doing. But in terms of the inner products of the angular momentum pieces, all that is just using, the regular angular momentum rules, that angular momentum basis. So that part doesn't change. See, everything reduces down to how things transform under rotations. That's what tells you about how the matrix elements will depend on these quantum numbers, J and M. So, all right, and if we do that, well, now it's easy. Why is it easy? Because this is the good basis right here, and this is the good basis. So that means this J prime has to be equal as J bar, and this M prime has to be equal as M bar. So that's pretty easy. It must mean that this is equal to C 1J QM. And now this J bar has to be equal to J prime. And this M bar has to be equal to M prime. Right? And so what's left over? What's left over is something that we might call it could depend on J, because we have these guys, and it could depend on J prime. It's whatever is left over that has any kind of dependence on our choice of V. So it's some number V that depends on J prime and J. And this is called the reduced matrix element. Okay, so we got rid of all of the M dependence in it. And we're left with something that doesn't depend on the rotations, right? This is the J prime and J, those are the total angular momentum quantum numbers. This doesn't depend on rotations. All of the pieces that are related to rotations are captured by this Clebsch-Gordon coefficient. And that's it. So you see and the more standard way to write this is J prime M prime of VQ, which again is one of these spherical, it's some spherical tensor operator. You can take any Cartesian vector like a position, the angular momentum itself. You can rewrite it in terms of its spherical components by just doing this transformation right here. And then when you look at the matrix elements in terms of angular momentum states, you'll get that any of these spherical tensor, spherical vector operators, they're just given by the following Clebsch-Gordon, QM, J prime, M prime, and then the thing that's left over is often written like this, where it's whatever pieces of the matrix of the operator, the matrix elements that don't depend on M and M prime at all. So you can calculate that reduced matrix element, by setting the M's equal to, by using some simplified methods that, pick an orientation for a coordinate system or something, right? It lets you reduce the computation of all these matrix elements to kind of complicated, right? You'd have to calculate separately for each value of M prime and M. Generally very difficult, but what the Wigner-Eckart theorem tells you is that all of the dependence on M prime and M is entirely captured by the Clebsch-Gordons, because the M and M prime, those are just depend on how things rotate. And the fact that we've written everything in terms of the spherical tensors, that already has kind of reduced or has identified how all of these objects rotate, right? Because we know exactly how they rotate because of how we, defined those unitary operators and how they work on the angular momentum states. And so this is a kind of a proof of like this one of the second most simplest version of the Wigner-Eckart. Of course, the scalar is probably the simplest of all of them. And now you can imagine that if you went through the same process for like an arbitrary spherical tensor, you could get something, you could get the full-fledged theorem, right? So let's do the full-fledged theorem. The full-fledged theorem is just that you have two states, and maybe they have extra quantum numbers of now an arbitrary spherical tensor, which I'm going to call KQ. Now I'm putting this Q up here, and this, so this is like the J, the total angular momentum, and this is like the M. I'm calling it K and Q, and I'm sandwiching in between these states. Then this thing is given by C, J, K. We're adding J to K, and we're getting out, and they have associated M and Q, and we're getting out something that's J prime M prime. Again, that's how you remember how this works. And then you get a reduced matrix element, which just depends on the pieces that don't rotate, which is the alpha and J, and the K portion of T, not the Q. The Q is the M thing that rotates around, and then like that. But you put double bars here sometimes because this is a reduced matrix element. So then, and this is the general theorem, the Wigner-Eckart theorem. All right, that was kind of a much more deliberate, I think, overview of Wigner-Eckart. Any questions about that? No? Okay. So you can, of course, do all kinds of fun tricks with this, or, you know, quote unquote fun. So one interesting trick you can do is, say you were looking at just the matrix elements for a fixed J. Say you were looking at J prime is equal to J. Then that's kind of interesting because the Wigner-Eckart theorem tells you that, say you were looking at a vector operator VQ JM, of course, then this becomes C1J QM. Now this is J M prime, and then this is J, this reduced matrix element. And now see, I don't even have to put a Q here because we know that this doesn't depend on Q, the M value. This is just whatever the matrix element is of the vector operator. And the interesting thing about this is that, of course, the angular momentum itself is also a vector. So if you were to look at the angular momentum components, they would, of course, satisfy the same kind of thing, 1J, QM, and J, M prime. And this would just be J. And so these matrix elements, they have to be proportional to each other. These are just numbers, and all of the kind of dependence on M and Q, it's buried in this Clebsch-Gordan coefficient, which is the same for both of these. So what you can do now, interestingly, is you can actually calculate the constant of proportionality by just playing tricks with bras and kets. And for instance, looking at J dotted into V, right? This is a scalar. So if we look at this guy sandwiched between JM, say, then we could stick in a completeness relation. So first of all, we can expand this in terms of components, right? This would be JK, VK, right? Sum over K. So, and then we could stick in a completeness relation and we would get the following, right? JM prime, JM prime, VK, JM. So we just stuck in a completeness relation here in the middle and expanded the dot product, right, as the sum of the components. And what does that mean? Well, we know from Wigner-Eckart that these coefficients, this one and this one, they're proportional to each other. So this must be equal to some constant of proportionality, which we'll call A. And then the rest of it is, right, JM, JK, JM prime, JM prime. And I can place this, I can replace this VK with just JK, right? Because I know that these matrix elements, the VQ and the JQ, these components, they're proportional to each other by the Wigner-Eckart theorem. So this just becomes that, right? And so this is some constant of proportionality. And what is this? We can do the completeness relation again, right? And remove this guy. And what you get is A sum over K. Well, you know, we can get rid of the K, actually. We can get rid of all of it. We can get rid of the sum over K and the sum over M prime because that just gives us completeness. And we're left with the expectation value of J squared, JM. But we know what that is. That's A, J, J plus 1. So that gives us a really nice thing, right? It tells you that the matrix element of a spherical tensor, a spherical vector operator, any one of them for a fixed J here is just equal to the constant of proportionality 1 over J plus 1 times the reduced matrix element of the dot product between J and V. That's what we're calculating here. And the rest is just these just the matrix elements of J. So this must be the constant of proportionality between these elements and these elements. So you can play tricks like that. Anyway, so that's an example of how you might use. But we'll do more of it when we do like the hydrogen atom and stuff next semester. We can use the Wigner-Eckart theorem to figure out how the energy eigenstates of the hydrogen atom, how can we transition between them, right, with various perturbations. We'll see that these matrix elements will tell us about transition rates between one state and another state. And if we can write the perturbation in terms of a spherical tensor like this, then we'll be able to know a lot of things about the, you know, like selection rules from jumping between different states, right? All right, now I'm really done. So now I'm really done with Wigner-Eckart. But any questions about Wigner-Eckart before I jump into sort of extra topic stuff? No?
And have you already made a selection for the extra topics that you're going to talk about here, or did we come to a conclusion of what topics?
Yeah, well, people wanted to learn about topology and relativistic quantum mechanics. There's some suggestions I got a suggestion, talk about gauge theory. I'll probably talk more about that second semester. But you know, topology is kind of everywhere if you look closely enough when we're talking about symmetries, because these concepts of representations are deeply connected to topology. So I kind of wanted to start there. And the idea is, remember that when we had a group G, remember we had this idea of representations of the group elements, that if you have some group elements in G, then in quantum mechanics, they are represented by unitary operators, which obey the same group properties, except that there might be some phase associated with them. So this is how we got the rotation group representations. We saw sometimes you pick up a minus sign, so it's not quite a representation of the group, because sometimes you pick up a minus sign, and that corresponded to the fermions. But in general, you have some, as it's called, a projective representation. Projective is whenever you have this phase factor. But what I didn't say, and how it's related to topology, is that it's always the case that for any group G, you can get a faithful representation of, meaning that no phase factor is there for its universal cover. So G has a universal cover. I'll tell you what that is in a moment. G bar, and this is the thing that has faithful representations. Has faithful representations in quantum mechanics, meaning that if we take any G1 bar, G2 bar in the universal covering group, then the group relationship always holds without any kind of funny phase business going on. And that's actually what Wigner's theorem is actually about. It's about representations of the universal cover of the group. And what a universal cover is, it's another group which all of the elements in G can be mapped to elements in G bar, but not necessarily one-to-one. So sometimes you will have multiple elements in the covering group that correspond to a single element of the universal of the original group. So for rotations, we saw that the rotations actually have a double cover, meaning that the covering group covers the original group twice, and that double coverage is what's responsible for the existence of fermions and boson spins of with half integer and integer angular momentum quantum numbers. And what the universal, so I didn't say this, the universal covering group is always simply connected. It covers this and it's simply connected, and those are its primary features, and these are topological in nature. Simply connected is that thing I was talking about with the belt trick, right? A simply connected space is one in which if you take a closed path inside that space, you can continuously deform it to a point. So if you take, say you're on a plane, right? And you take, and say the plane represents all different group elements, and if you take any closed loop in the plane, right, you can continuously deform the loop to shrink it to a point. That's always allowed That's what a simply connected space is one in which any closed loop is contractible to a point. That's a very topological thing, right? Because, maybe the kind of common thing you hear about topology is that, topologically equivalent spaces are ones with, a continuous homeomorphism. So people give you an example of like a coffee cup, right? And a donut. And these are the same topologically because you can continuously deform the coffee cup until it, has the same shape as a donut. So there's some continuous invertible function that takes you from the donut to the coffee cup. You can continuously kind of stretch the handle of the coffee cup and flatten the cup part, right? And then slowly transform it into a donut. That's the idea. So this idea of the covering space is very similar. The fact that it's simply connected is a kind of homeomorphic property of closed paths in the space. And why is that important is because, remember, from Stone's theorem, we saw that group elements are generally, kind of generated by some exponentiated generator like jx, jy, jz. And if you think about it, what that means, it means that all those group elements, they're smoothly connected to the identity because I can sort of take theta to 0, right? And then this guy will just be the identity. So all of the group elements that we generate by exponentiating these little generators, which form some commutation relations like this, JZ, right? Those exponentiated operators, the group that's formed there is topologically very simple. It's simply connected because all of the group elements can be sort of smoothly connected to the identity. So really, when you're deriving like the Lie algebra that we derived for these angular momentum guys, what you're really doing is deriving the algebra of the covering group. The actual structure of the rotations is more complicated than that because we know there are, because we know that the space is not simply connected. So that's a kind of subtle thing, and it really, it tells you a lot about the actual representations of the group and how it plays out in quantum mechanics. So I just wanted to give some examples of groups and their universal covering spaces. There's three main ones that are kind of relevant for physics. One is, of course, the rotations. The universal covering for that is SU2. And the mapping, of course, is 2 to 1, right? So for each element of SO3, every rotation, there's 2 different kinds of elements of SU2. It's a double cover. So this group covers this guy twice. And that double coverage is can be labeled by that minus sign that you get if you rotate by 2 pi. If you get a minus sign after rotating by 2 pi, then you're on like one of the covers, and then if you don't, then you're on the other one. So it's kind of label of the double coverage. And the double cover aspect of this is why we have fermions and bosons, those kinds of particles. And you can actually see why this guy is simply connected, because if you recall, an element of SU2, what's SU2? It's the special determinant 1 group of unitary matrices, or 2 by 2 complex matrices. So all these guys, they look like the following. It looks like alpha, alpha star, and beta minus beta star. Like that. And there's a constraint that the determinant is 1, and that constraint comes down to this. So we already see a lot about this. Just like the rotations, there's 3 parameters that you need. So like the real and imaginary parts of alpha and beta, so that's 4, and then there's a constraint. So it subtracts 4 minus 1 is 3. So there's 3 parameters for the group, just like there's 3 parameters for SO3, the rotations, the 3 Euler angles, or if you want the direction in which you're rotating and the angle. But you can actually see now why topologically this is simply connected. If all of your group elements look like this, then these are complex numbers. And if we write out the real and imaginary parts, right, this becomes real part of alpha squared, imaginary part of alpha squared, plus real part of beta squared. It's equal to 1. This describes, and these are all just numbers ranging from minus infinity to infinity. Under this constraint, this describes the surface of a sphere in 4 dimensions. A unit sphere, this is a unit sphere surface, right? In 4 dimensions. Or if you want, it's called S3. That's the group. And the surface of a sphere is a very simple space. You take any surface of a sphere, right? You take a little loop on it. You can always contract all these guys to a point. So it's simply connected. Same thing, if surface of a sphere in 4 dimensions is also going to be simply connected. So the universal cover here, as promised, is simply connected. And you might wonder, what's the mapping between elements of SO3 and SU2? Well, we know what they are, actually. If this is the SU2 element, we know that an element of SO3 is labeled by an angle theta and an n hat, a direction which we're rotating. Remember, you pick the direction you're rotating and then the amount that you're rotating. Any element of SU2 you can actually write as the identity times the cosine of theta over 2 minus I sigma dot n hat sine of theta over 2. So given any element of SO3, I can construct for you an element of SU2. And the only other part that remains to be shown, and maybe I'll show later, but it's sort of not part of the extra topics because it's more of, actually it's closer related. This used to be a homework problem, is to show that the mapping really is 2 to 1, that it's a double coverage, that there's 2 of these SU2 elements for every actual rotation. But we kind of know that that has to be the case because of this theta over 2 business. We know that there'll be elements where a rotation by 2 pi, it gives you a minus sign. And that's what you get actually in SU2. So if you actually think of this unit sphere surface, the way to think about the actual rotations there is that the rotations by 0 are like at the North Pole, and rotations by 2 pi are at the South Pole. Those are the corresponding group elements on the surface of the sphere. But again, it's a surface of a sphere in 4 dimensions. So a lot of people get confused about the relationship, because see, there's a lot of stuff going on here. You have SU2, which it looks like the surface of a sphere, but it's in 4 dimensions. And then you have SO3, which, remember I told you, is a ball, a solid sphere with radius pi, right? And there you saw that you have paths that are not simply connected because and with antipodal points identified. So if you have a path here that goes from one pole to the other through the ball, you can't control. This is a closed loop because the poles are identified. This is not simply connected, but this guy is, because the poles are not identified here. It's just the surface of a sphere in 4 dimensions. So any loop you have in here is contractible to a point. But this is the universal cover of SU2. And the idea is it's the representations of your group of interest. They're projective, meaning they can pick up a phase. And to get rid of that phase, you have to go to the universal cover. And so it's the properties of the cover that actually tell you about the projective representations of the group, meaning it tells you about the different kinds of particles you can have here. So this tells you, because it's a double cover, that you get fermions and bosons for 3D space. Now, for those of you interested in condensed matter, there's a lot of work now, right, on anyons and funny statistics of excitations, right, in condensed matter systems. Well, all those things are, in my mind, they're a little bit silly because they're all surface phenomena. The only way that happens is because you have a group which is SO2, which is rotations in the plane. The covering group of SO2 is the real numbers. And you can see that very easily. Any element of SO2, it's a rotation in 2D. I can write it as e to the I theta because, right, any rotation I can just specify in the complex plane like that by like a phase. And so this theta here, that is a real number, right? And that's the covering group because the real number, because that's the thing that's simply connected, right? The real numbers are simply connected because if you have a path along the real line, right, that sort of lines in on itself, you can always contract that to a point. But you can't contract a rotation, a closed path in 2D space, right? Because if you have a rotation in 2D, say in the XY plane here, and you rotate around, the number of times you rotate around the origin, that prevents you from continuously deforming the closed path to just the point, right? If you have a pencil or something and you rotate it around like twice, I can't continuously deform that rotation, that set of rotations to a point because there'll be some integer number of times which I went around the origin, moved around the origin. Or if you want to think of it another way, the continuous deformations can be thought of as take a pole in the ground and you attach a string to it, and then you rotate the string around the pole, and those are the rotations. And if you have a closed path in this rotation space, you go back to where you started, you can't continuously deform that to doing nothing, right? Because you'll get the string tangled up, however many times you went around the origin. That's exactly the same as in 3D, the fact that my hand gets all messed up when I rotate by 2 pi. That's kind of like having the string get tangled up once in 2D, but in 2D you can do more tangles. You can tangle it over and over again, and that gives you an infinite covering space, right? You cover this space of rotations by the universal cover, not just twice like in 3D, but actually an infinite number of times. And so that means that you can get a projective representation, right, in 2 dimensions of the rotations that has an arbitrary phase factor, not just plus or minus 1, but any phase, because of that infinite coverage by the universal cover. And so that means that you can get, instead of having just integer and half integer type particles, spin particles, in 2D, you can get an arbitrary spin, like an arbitrary real number. And that leads to the concept of, these exotic particle excitations. Condensed matter people like these days, they're just studying, 2-dimensional phenomena. That's the only dimension in which that's possible. In 3 dimensions, you only get fermions and bosons as representations of the rotation group. So yeah, so that's the other relevant example. This is for condensed matter folks out there. All right, and the other interesting example, of course, is the Lorentz transformations. Where the Lorentz transformations, well, that's the group there is SO31. Yeah, sometimes they add a little plus sign. This is what this is. It's all of the transformations that keep the magnitude of your 4 vectors, in special relativity constant. So that includes the spatial rotations, but it also includes boosts. So there's 3 rotations, so it includes SO3 as a subgroup of it, but it also includes the 3 boosts. So it's a total 6-dimensional space. And the covering group, as it turns out, is it's kind of like SU2, but not. It's actually 2 copies of SU2, but the actual group is SL2C. This is a special group of linear transformations. So special means the determinant is 1. And the linear part means that it's invertible matrices. So it's the element, it's 2 by 2 complex matrices that are invertible. Of course, that's a much weaker constraint than saying they're unitary, right? So it's a bigger group than SU2. And what you can actually show is that it's isomorphic to SU2 cross SU2. It's 2 copies of SU2. And this is really the fundamental reason why you have 2 different kinds of particles in relativistic quantum mechanics, right? You have the particle and you have the antiparticle. So it sort of you might already start guessing just from the group theory that instead of just a single kind of spin 1/2, you can have 2 different kinds of spin 1/2 particles, like a left-handed and a right-handed one. So that's, you see, it gets very powerful applying these ideas to topological properties of groups to the groups associated with physical symmetries. So the thing we could do now, since people wanted to, well, at least one of you wanted to see what, relativistic quantum mechanics looks like. We can talk about this SO3-1 space a little bit, what it is, how it's generated. I can show you why you get SU2 cross SU2 for the covering group. But any questions, though, before I move on to that? Incidentally, the way you can get around these constraints, right? So we now see that, in 3 dimensions, you're kind of doomed to either looking at fermions and bosons. Well, the way you can, of course, escape this conclusion is if you allow your objects to be extended. And that's basically what is accomplished in string theory. And then you can have sort of internal properties of your particles, if they're extended objects, then they'll have their own associated symmetries. And string theory, a lot of that, a lot of time in string theory is spent studying ever more exotic groups associated with those internal properties of the extended objects. But a lot of the sort of baby steps are kind of already here in what I'm showing you.
Yeah, I think it was very helpful considering, you go to the Google and go to Wiki and they have a whole thing that kind of lets you help explain it. That's why, that's like these videos, that's why it's important that I can get access to them later on, as your explanations do help. So.
All right, good. So, well, if there are no questions about it, of course, I gotta say I'm not particularly an expert, but I don't know. I'll answer what I can, I guess.
So I know this is off topic then, but your research is more biophysics though, right? So in relationship to like isn't it biophysics? Is that correct?
I would say it's more like statistical mechanics, but yeah, it's
Oh, okay.
applied to bio, yeah.
So now, this you use this part of it pretty often then, since you're using a lot of in biology. You have the surface and topologies and stuff. So I was wondering, is this something that you're pretty familiar with then? I mean, per se, do you use this in your research, or just more just analysis with computer programs and stuff like that?
I would say this is kind of going on in the background. I'm not too familiar with it, but I'll tell you this. A lot of biological systems have kind of exotic phases, right? So you know that you have the solid, liquid, and gas, right? And phases themselves are, of course, characterized by symmetries. Any particular solid, you can characterize by some discrete translation symmetry associated with the unit cell solid. Similarly, in biology, there are some phases like the nematic liquid crystal, other phases where they have some other symmetries, namely there's some orientational orders, say, where you have cylindrical like molecules which all align in a particular direction. Well, if you think about the symmetry group associated with that, that must be some kind of orientational group that sort of gives you an overall orientation, but doesn't care about the direction.
Mm-hmm.
So it's not a vector, it's called a director. And the group associated with that is not really the rotations. So it's not really like a circle, because that's a vector, right? It points in a particular direction along the circle. It's really a director. So it's a circle with the antipodal points identified. And so that's a group. And studying the topological properties of that group tells you about things like, what do the defects look like inside your phase? Like if you have a defect in the orientation of the liquid crystal, that has topological properties which you can understand by studying the associated group of symmetries associated with that phase. So that's the kind of thing that you can apply this to in condensed. And then this is a more general statement about condensed matter, actually.
Yeah,
that's what it's useful for there.
Yeah, I thought that's what you were getting more into. You're saying the crystal structures and stuff. I was saying, oh, that's condensed matter. Okay.
Yeah, so the topological properties of the associated symmetry groups can tell you about things like defects.
Yeah.
Or other things like band structure for you solid state people out there, I guess. I'm of course less familiar with that because I don't deal with electrons all that often. But all right, so I guess we're out of time. But next time, what I'll do maybe is pull in on SO31.
Okay.
Unless I get some emails saying that they demand a result, we'll focus in a little bit, and I'll maybe derive for you. So what the idea here is, I should say this before you all take off. So the reason why we have this kind of Hamiltonian, right, for all of our problems is because we're actually relying on Galilean symmetry. We're relying on not the Lorentz symmetry, but just the symmetry under just regular, non-relativistic Galilean boosts. So without all this four vector business. But when you have Lorentz symmetry, then your Hamiltonian, it doesn't have the same sort of properties. You want to it'll have a different form because it has to now be consistent with the Lorentz invariance with this group SO31. So next time what I'll do is I'll focus in on SO31, tell you about how it's generated, do the little T matrix stuff that we did for the rotation group. And then I'll show you what the associated Schrodinger equation would have to be in order for it to be consistent with the Lorentz symmetry. And that'll lead us to the Klein-Gordon and Dirac equation.